Welcome back, guys. Today we're going to be taking a look at 2016 N4. So the problem says we have n, m, k, l as positive integers with n not equal to 1, such that n to the k plus m times n to the l plus 1 divides n to the k plus l minus 1. And we want to prove that either m equals 1 and l equals 2k, or l divides k, and m is equal to n to the k minus l minus 1 over n to the l minus 1. So that was a mouthful, but let's first write the condition we have. We actually only have one condition, which is that n to the k plus m times n to the l plus 1 divides n to the k plus l minus 1. And so given this one condition, what we want to do is we want to prove that one of these holds true. And if you think about this for a bit longer, you realize that these are actually just the solutions to the thing. If you were to plug this into this, you'll see that the divisibility does indeed hold. And so these are actually just two classes of solutions. And our task is just to show that these two classes are the only classes of solution to our divisibility right here. And so this problem is somewhat like a Diophantine equation, where you're given some relationship, except that it's not a Diophantine equation, it's a divisibility relationship, and you want to find all the solutions, but they already tell you that the solutions are these. So anyways, just a little bit of dissecting the problem. So now we can actually get started to working on this problem. And so if you try to plug each of these in, for example, if you try to plug the first one in, then you should get that the ratio should be equal to, I think, it should be equal to n to the k minus 1. So n to the k minus 1 multiplied by this will be equal to this, so it does indeed divide it. And if you take this second one, the quotient should be n to the l minus 1 if you were to check for yourself. The reason we're doing this is that this gives us a bit of a hint as to what might happen here. So for example, the quotient here might also be something similar to that. And if you were to look at the size of these two things, well, you can see that that's quite consistent. For example, if I were to multiply this by n to the l, then this would get to n to the k plus l. And so, yeah, that's quite consistent with whatever that is over there. Okay, and so whenever we have some divisibilities like this, there are some paths we can take, per se. So the first thing is we can look at some factors. For example, if we have some prime factor p on the left-hand side, then since p divides this, we know that p must also divide this. If we have some prime factor p on the right-hand side, p divides this. Well, it doesn't tell us p divides this, but what it can tell us is that, for example, if p does not divide this, then we can take p out of this, so we get n to the k plus l minus 1 over p, and the left-hand side should still divide it because p is, in a sense, useless in this case. Yeah, so that's the first thing we can do. We can analyze prime factors, which is a more number-theoretic way to go at things. In contrast, a more algebraic way to look at things is to do bounding, or I'm going to call it size comparison because I feel like that's more intuitive. So we are comparing the size of the two things. For example, if this thing divides this, then obviously this thing needs to be bigger or greater than equal to. And by the way, this can't be 0 because we have restricted n not equal to 1. And so yeah, we can do size comparison. And also a lot of times we can actually combine these two methods, so we're using a combination of them, where, for example, I may be able to analyze some factor. This has a p that does not divide this, and then we can divide this by p, and then we get that the left-hand side still has to divide the right-hand side, so then we can use size comparison again. So things like that. And what we're going to do in this problem is that we can notice that you see there's a plus 1 over here, there's a minus 1 over here, and the rest are all multiples of n. And so maybe that will give us a hint, maybe. So what I mean is that, for example, let's assume that k is bigger than L. Then, for example, this side is congruent to 1 mod n to the L, because all of these are divisible by n to the L, and this side is congruent to -1, so n to the L minus 1 mod n to the L. And if we want to multiply something to get from this to this, then the thing we are multiplying must be congruent to n to the L minus 1 mod n to the L. So this is about multiplicative inverses in a sense. You're just doing n to the L minus 1 divided by 1, except in modulo. So this would be multiplied by the multiplicative inverse of 1, which is still just 1. Anyways, the reason this is helpful is that we can get a trivial lower bound for this, which is that this quotient must be at least n to the L minus 1. So with this, we can get a bound, and then we can actually do size comparison. If we take a look and verify back at, for example, what we have over here, we have an n to the L minus 1, it actually looks quite consistent because n to the L minus 1 looks like a pretty good bound for this thing right here. So let's try to follow that idea through. But the first thing we need to do with that idea is to actually do a bit of case analysis, because I had to assume k is greater than L. If k is not, then I can't say that n to the L divides n to the k. So we're going to do some cases. And if we take a look at what's happening over here, this is basically two cases. And the first case is k is greater than L. The second case is L is greater than k, or L is greater than equal to k. Okay, so let's do the second case first. L is greater than equal to k. So what we're going to do in this, like we just mentioned, is that we're going to take mod n to the k on both sides. So the left hand side, which is n to the k plus m times n to the L plus 1, this thing should be congruent to 1 mod n to the k. The right hand side should be congruent to -1, should be congruent to negative, or just n to the k minus 1 mod n to the k. So like we talked about, the quotient needs to be congruent to n to the k minus 1 mod n to the k, which means that it must be able to be written as, so this is a bijective condition, it must be able to be written as s times n to the k minus 1 for some s, for some positive integer s. Okay, and so what we can do is, this is a quotient, so obviously we should just multiply this thing and see what we can get. So we want to multiply n to the k plus m n to the L plus 1 by s n to the k minus 1. This should be equal to n to the k plus L minus 1. Alright, so if we expand this, what we should get is we should get s n to the 2k plus sm n to the k plus L. By the way, L should be greater than or equal to k up there, so this thing should be bigger than that in a sense, plus s n to the k, and then we should get minus n to the k minus m times n to the L minus 1, and is equal to this. So we can simplify a bit. For example, the minus 1 can go away, and then we should be able to combine some more like terms. For example, we should get sm minus 1 times n to the k plus L plus, let's do s times n to the 2k plus s minus 1 n to the k minus m n to the L. This thing is equal to 0. Okay, so all that algebra, we get whatever is left with this. And so as we discussed from above, we should have that s is equal to 1. Otherwise, this should be too big. So for example, if we say s is greater than or equal to 2, then we should be able to get some contradictions right here. For example, the only minus term is mn to the L. And so if we take a look at this, then this thing should be greater than or equal to 2m minus 1 multiplied by n to the k plus L. And then this thing is obviously, it's positive. This thing's also positive. And this thing is whatever this is. And so first of all, notice that since m is greater than or equal to 1, it's a positive integer, we have that 2m minus 1 is at least m, and n to the k plus l is bigger than n to the l. Hence, we must have that s is less than 2, because this is a contradiction. And the only way for s to be less than 2 is we have s is equal to 1. Then we should be able to plug and chug everything in here. For example, what we get here is m minus 1 times n to the k plus l plus s times n to the 2, or s is just 1, so plus n to the 2k plus, this is 0, so we just do minus m times n to the l. This is equal to 0. Okay, so again, we hypothesized that m should also be equal to 1, because if we look at the solution here, m has to be equal to 1. So same thing, we just assume for the sake of contradiction that m is greater than or equal to 2. Then we want to compare these things and probably get a contradiction, because this thing looks quite big. And if we look at this, m minus 1, maybe we want to prove this is greater than or equal to m times n to the l. If we were to just rearrange things a bit, we should get n to the k greater than or equal to m over m minus 1. And well, obviously this is true. N is greater than or equal to 2 and k is greater than or equal to 1. So n to the k is at least 2, and this thing, well, it's obviously less than or equal to 2. And so yeah, it's true. And then so this thing is at least 0, there's some, and then this thing is obviously at least 0. So the thing cannot be equal to 0. No, this thing is strictly greater than 0, so it cannot be equal to 0. Okay, so we get that m must be equal to 1, and so in that case, we should have that, if m is equal to 1, the first term has m minus 1, will just go away. And so we should be left with n to the 2k minus m to the n to the l is equal to 0, which just means that l is equal to 2k. Alright, so m equals 1, l equals 2k, that's our conclusion, which if we check up here is actually exactly the same as this one. So yeah, that matches, and then we have done the first case. And there should be no holes here. Everything was comprehensive. So for the second case, our first case was l is greater than or equal to k, that's case 1. Let's do our second case, which will be k is greater than l. If we look at this, then we should get something looking a bit like this. M should be equal to whatever this thing is. But we don't need to worry about that. We can just take a look at this thing right now. So I'm going to copy that thing down again because I may not be able to remember it. Okay, so this time, following what we previously discussed, we should consider mod n to the l. So this left-hand side, this thing will just be congruent to 1 mod n to the l. This right-hand side is congruent to n to the l minus 1. And so, whatever we need to multiply should be congruent to n to the l minus 1 mod n to the l. So again, we can write it in the form s times n to the l minus 1. That is the quotient with s greater than or equal to 1, and we should make s equal to 1. So similarly, we can just multiply the thing out again, and we should get n to the k plus m n to the l minus 1, or plus 1, times s times n to the l minus 1. This is equal to s times n to the k plus l plus sm n to the 2l plus s times n to the l minus n to the k minus m times n to the l minus 1, and this should eventually be equal to n to the k plus l minus 1. So the minus 1 cancels out again. If we rearrange the terms, we get s minus 1 times n to the k plus l plus sm n to the 2l plus, what should it be now? S minus m times n to the l, and then minus n to the k should just sit there by itself. Okay. And again, in this case, this is actually the only subtraction term. Actually, this thing is also being subtracted. But like if m was greater than s, this thing is being subtracted. So we also need to take that into account. But if we take a look at Sm n to the 2l, that's actually quite big. Alright, so in the same spirit as last time, let's first assume for the sake of contradiction, s is greater than or equal to 2. We can first use a trivial bound to get that s minus 1. So this first term, s minus 1 times n to the k plus l, is trivially greater than n to the k. So we can already get rid of one of these negatives. So maybe we just prove that this thing is greater than the negative of this thing. So Sm n to the 2l, we want to prove this is greater than or equal to m minus s times n to the l. Similarly, we can just move these things over again. N to the l is greater than or equal to m minus s over Sm. So we probably want to bound this thing from above. And okay, so this thing is maximized when s is minimized on the top so that m minus s is as big as possible, and also the bottom is as big as possible, or as small as possible. So m minus s over Sm is less than or equal to m minus 2 over 2m. And since we have that n to the l is greater than or equal to 2 like last time, so this thing is obviously not greater than or equal to 2. This thing is obviously less than 2. And so we can get our bound like this. Alright, so that's confirmed. So, like last time, we must have s equal to 1. Let me just quickly get rid of this thing. Alright. So we have s is equal to 1, and so this thing should cancel out. And then this we should get m n 2 to the l. This should be 1 minus m n to the l minus n to the k is equal to 0. Alright, so we just group everything over, and we should be able to solve for m using the other variables. So for example, here we should have m times n to the 2l minus 1, yes, is equal to n to the k minus 1, yeah. If we divide m to the k minus n to the l, if we divide this thing over, we should get m is equal to n to the k minus n to the l over n to the 2l minus 1. And, wait, by the way, this thing should be n to the l minus n to the l. And if we notice, there's an n to the l on everything, so we can just cancel that out. And we get n to the k minus l minus 1 over n to the l minus 1. Alright, and so this is actually looking exactly like our case over here. It's looking like this. And for the l divided by k, since m is an integer, we must have this thing should be an integer, which just means that l divides k minus l, so l divides k. Yeah, so that is the conclusion of our second case, and we have done both cases and we solved the problem. So, reflection for this problem, we use the intuition for the size comparison in this case. For example, we're taking a look and see that this is 1 mod n to the k and this is negative 1 mod n to the k. So we can actually bound the quotient from below. So that's very helpful because it can give us a upper bound or a lower bound for whatever this thing is. And we can use that to do size comparison, which is further supported by the fact that whatever this thing is actually really close to the bound that we're getting. And so the takeaway from this problem is definitely to how to deal with these divisibility problems, which is number 1 with factors and number 2 with size comparisons. And also, like mentioned before, we can obviously do some sort of combination of both of them, which in this case turned out to be really helpful.